Just getting into low Earth orbit currently requires a lot of fuel, effort, and money, which is why many astrologists, idealists, and physicists have created alternatives to solve this problem, such as the mass driver, two twin rails which electromagnetically accelerate rockets to great speeds, or space tethers, massive cables with hooks on the end that rotate and catch the rockets and swing them up into orbit. However, these ideas require very specific conditions which cannot be easily fulfilled on Earth. For example, the mass driver has g-force and length inversely proportional, and there are very few places where a mass driver can be put that is long enough for the g-force to be survivable. For a space company, it is not attractive committing to a completely unorthodox method without proof that is far superior. Other ideas like orbital rings, space elevators, and balloons are all unproven technologies. However, some agencies, such as the national Chinese and Japanese space organizations, have separately committed to building space tethers by 2045 and 2050. When we considered the problem, we realized that most of these other ideas are ways of generating incredible amounts of speed and energy. So we first considered energy by thinking about the most powerful energy humanity has at their disposal: nuclear, fission, and fusion, which come from unstable atoms being divided and merged. They are almost direct opposites of each other, so we thought about combining them in a fission/fusion reactor that could take rockets to great distances. The only problem with this is that nuclear fusion uses the heavy hydrogen isotopes, deuterium and tritium, which do not naturally occur. So when merged, these molecules might not reassemble into the same structure, breaking the fission/fusion cycle. Next, we thought about a stratospheric/mesospheric orbital station, which could use hovercrafts to reach it, and use space planes to access further above. This would be similar to the ISS, just at a significantly lower orbit. Whilst this may seem promising, the atmospheric drag of the orbital station would need to be compensated by a lot of costly energy, creating new problems while solving one. Our final idea was that of a multi-stage pre-takeoff accelerator, or MCTA for short. As this is the idea we chose for the reasons that will be stated shortly, you can see the initial model of the designs below. It works off the mathematical principle of centripetal and tangential acceleration. The initial stage is a centripetal accelerator, which uses the centripetal acceleration as defined by the equation you see on the screen. When the cylinder rotates, the rocket gains centripetal acceleration and the velocity increases. This can be used to accelerate the rocket to incredible velocities, depending on how long it's in the cylinder for. The second stage utilizes tangential acceleration, which is the linear acceleration in the direction that is at a tangent to the circle at the moment. The final stage is a magnetic accelerator, which is similar to the concept of a mass driver, except it requires a fraction of the track due to it only being a small portion of the total acceleration. Centripetal and tangential acceleration are the two forms of acceleration gained by an object pinned to the edge of a spinning body. Centripetal acceleration being the acceleration gained inwards, and tangential acceleration being the acceleration gained in the direction of motion. The concept of a mass driver system uses magnetic acceleration to increase the rocket speed. This follows an almost identical pattern. After the rocket is accelerated to nearly 90% of its takeoff speed on the CT accelerator, the magnetic section brings the velocity to over 20,000 km per hour. This is achieved using electromagnets along the side of the track during the second stage of acceleration.